Welcome back. In the last few videos we have seen how to reduce second order linear partial differential equation into a canonical form. That is one of these three typical equations. One is a wave equation, other one heat equation and a Laplace equation. So these are the three types, which is hyperbolic, parabolic and elliptic type of equations. So today we will just in this video we will have initial or boundary value problems, initial and boundary value problems for a wave equation to start with. So we will start with the wave equation and we give the boundary, we consider the domains. In certain domains we will try to solve the wave equation, and then if it is required, if you have a boundary you provide a boundary data, and if it is and you also provide initial data, and we will see the methods how to solve these kind of problems. Okay. So to start with the wave equation, so we consider a wave equation. So you can see the wave equation is we have already solved how to solve it. We have seen utt minus c square uxx equal to 0. This is spatially you have one dimension. So you have x is in the spatial variable, that is full domain, nothing is given. So that means it is a full domain, and t is the time, that is t is positive. So you have two variables x and t. X is a spatial variable and t is a time variable. So because t is time, t is always you take it as positive. So you have some kind of domain is, this is t and this is x. So this is one dimension because the spatial variable is one dimension. So this is a one dimensional evolution equation, so wave equation. Okay. Evolution means as time goes you see the evolution of the displacement of the dependent variable u of x t. Okay. It depends on the time. As time goes you are trying to find what is the value, okay, what is the displacement of this infinite string. So this is a model for an infinite string having c is if you take it as t is the tension of the string and rho is the density of the string. If you consider this uniform density of the string, t by rho is actually c. So t by rho actually should say a root of this is actually your c. So c square is actually where t is tension, string tension, magnitude of tension, magnitude of string tension. Okay. So you can say simply tension, and rho is density, string density. So uniform, so if you have infinite string, you can model it model that infinite string with this wave equation, that is the one dimensional wave equation. So we can write one dimension. So actually one dimensional wave equation. So because spatial variable is only one dimension. So this is your equation, you have your domain. Now what is the boundary? You see that you have infinite is unbounded domain, that is x is at infinity, but you see that at t equal to 0 you should provide, that is actually kind of boundary if you see as a full domain as a xt domain, but as physically this is initial values, initial data when you giving at t equal to 0, that is initial data. Okay. You do not call it boundary data because this is not corresponding to the spatial variable x. So you have initial data at t equal to 0. So initial data is ux0 is given as, so that means you provide at time t equal to 0 what is the displacement of your string, that you can take it as some given function fx for every x belongs to R. And also because it is a second order, you have a t derivative is in the second order, we should provide two conditions for the initial data. So you provide the velocity of this string at t equal to 0, x0. So if you see this at t equal to 0, so it is like du by dt, that is why I am calling velocity at t equal to 0. So that is you call this some g of x given function at every point of the string, infinite string. So, basically you start with this domain, x is in full R, full x takes all the real values, okay. X is full real axis. If this is your domain, we have to solve this equation with this initial data. So, we will try to solve this. This is called the D'Alembert solution. So, D'Alembert's the solution is given the solution. So, named after D'Alembert's. A solution is how do we do this? How do we, first of all you have to solve just like ordinary differential equations. This is like a boundary data. So, this is some given data at the boundary at t equal to 0. This is the only boundary you have. So, first you have to find the general solution of this equation and then you apply these boundary conditions, get those arbitrary functions, you just fix it based on the initial data. That is how you get the solution of this problem. So, this is the initial value problem. So, what we do is we have already seen how to reduce this into the canonical form u t t minus c square u x x equal to 0. This equation, if I choose xi as x minus c t, eta as x plus c t, we have seen that what you get is u xi eta equal to 0, okay. The equation reduces a given PD wave equation reduces to u xi eta equal to 0. This is what we have seen, and immediately if you try to solve this equation, so you have seen that u xi eta, if you simply integrate both sides that we have seen in the last video, you can see that C1 of xi, that is x minus c t, plus C2 of x plus c t. So, C1 C2 are, where C1 C2 are arbitrary functions. So, once you have this, this is your general solution of the wave equation, that is what we have seen, okay. This is the general solution, of wave equation. Now, we simply would try to apply these boundary conditions, okay. So, what is your boundary condition? ux0 is fx. So, ux0, so you try to so once you get a general solution in the new variables, it is xt, this is what it is. If you write u of xi eta, that is c1 xi plus c2 eta, okay, and once you bring it to the new old variables, u of xt is, this is your general solution of the given wave equation. Now, you apply this initial condition, u at x0 is equal to fx. So, fx equal to u at x equal to 0, that is c1x plus c2x. What happens to ut at x equal to 0? So, what is this ut at x equal to 0? That is dou u by dou t at x equal to 0, at t equal to 0, okay. So, what is this one? Dou u by dou t at t equal to 0 is minus c1 of x minus c t at t equal to 0. So, c1x plus c2 times x, okay. So, this is actually equal to, c is common, you have minus c1x plus c2x. So, what is this one? This is actually given as ut at x0, this is my gx, that is what is given, okay. This is what is your second initial condition, this is true for every x. So, this implies g of x equal to c times minus c1x plus c2x. From this you can actually sorry, so this is not the way, so made a mistake. So, how do I get this dou u by dou t? So, this is c1 dash dou u by dou t is basically see how do you calculate dou u by dou t? This is like dou u by dou x minus ct into dou x minus ct divided by dou t. This whole thing now we put at t equal to 0 plus dou this u is c1, first c1 function, c1 of x minus ct, okay. And similarly dou c2 of x plus ct divided by dou x minus ct, x plus ct into dou x plus ct divided by dou t, this whole thing put t equal to 0, that is what it is. So, this is equal to, now we put t equal to 0, this is simply c1 is actually what you see is dou c1 by dou x when you put t equal to 0, okay. That is simply, now c1 is a function of x. So, what is this? This is simply c1 dash of x, and what you get here is minus c. When you put t equal to 0, that is simply minus c times minus c times 1, okay, and you put t equal to 0, that is what you will get, okay. So, this one and plus dou c2 of x divided by dou x into c, and if this one when you put t equal to 0 you get c. So, this together will give me, now this you can write now minus c1 dash x plus c2 dash of x. So, this is what is my left hand side is gx. So, this is my second equation. So, this is your first equation, this is your second equation. So, second equation, I do not call it second equation, you do one more step. Now, we try to differentiate this, not differentiation. So, you try to integrate this, you will try to integrate this equation, okay. You try to integrate, this is the function g of x, x belongs to full R. So, you choose some, so you have initial value problem t equal to 0. So, anyway, so you can just integrate from any fixed point x naught in your x domain. X domain is this real line, okay. You can choose any point x naught to x, x is arbitrary value. So, if you integrate from any x naught to x, g of t, I am calling it gx dx, but I am calling it gt gs ds, okay. It is just a dummy variable equal to c times minus integral x naught to x c1 dash of s ds plus integral x naught to x c2 dash of s ds. So, this is nothing but c times, okay. So, you can write here. So, say that c times 1 by c. So, you bring this c 1 by c. So, you have integral x naught to x g of s ds equal to, so this minus, so if you, this is the derivative, so it will become c1 of x minus, here the upper term will give you c2 of x. Now, here bottom you see that it will be c1 at x naught, and here minus c2 at x naught, this is what you will get. So, this is what is your equation. So, right. So, this gives me an equation in C1 and C2, that is minus C1x plus C2x equal to 1 by C integral x naught to x g of s ds plus C2 x naught minus C1 of x naught. So, you bring this to the other side, so that this is what you see, this is your equation number 2. So, from 1 and 2 C1 plus C2 equal to f minus C1 plus C2 is this one. So, if you add 1 plus 2 gives, what do you get if you do 2 times C2x equal to, what if you add right side. So, you have fx plus this part, fx plus 1 by c integral x naught to x g of s ds plus 1 by c2 of at x naught minus c1 at x naught. So, now you divide both sides 1 by 2, 1 by 2 and 1 by 2. Okay. Now, you take the difference 1 minus 2 gives, you get c1 of x, 2 times c1 of x actually equal to fx minus 1 by c integral x naught to x g of s ds minus c2 at x naught minus c1 of at x naught. This is what you get. If you simply 1 minus 2 is c1 plus c2 minus plus, this becomes 2 c1. So, fx minus right hand side fx minus this part. So, this is what you will get. So, now again you divide with this side. So, you have this one, you have this one. Okay. Now, we see that c2x c1x is this one. So, what I need, I have the general solution as c1 at x minus ct, c2 at x plus ct. So, you will try to write what is your u of xt directly. U of xt is c1 at x minus ct plus c2 at x plus ct. So, what is c1 at x plus x minus ct? You put it here. In the place of x, you put x minus ct. So, what you get is f at x minus ct plus 1 by 2 c x naught to x minus ct gs ds plus half, this is a constant. So, that will not change. Okay. This one half c2 at x naught minus c1 at x naught. Now, what is the next one? So, plus half f at x plus ct, which I am writing c2. Okay. c2 at x plus ct, c1 is this. So, c1 should be minus. So, c1 if you write, this is minus and this is going to be minus. So, c1 I wrote, now I am writing plus c2. c2 is half x plus ct plus 1 by 2 c x naught to x plus ct gs ds, and this is plus half, this is anyway constant c2 x x naught minus c1 at x naught. So, this gets cancelled. What you see is simply you combine these two terms, this one and this one. If you combine, you see that f at x minus ct plus f at x plus ct, half of that, and then this one you can write x minus ct to x naught. Okay. X minus ct to x naught, if you do, so this things this you can write 1 by, so 1 by 2 c is common. What you have here is first term, this term you try to write is going, it was actually minus, it is going to be plus when you write x minus ct to x naught gs ds, and this one you have from x naught to x plus ct gs ds. So, if we combine it, now we can combine it and write this as x plus ct. Okay. So, this is what you have. So, this is what is my u of xt. So, this is the solution of the initial value problem that I defined. Okay. So, this is your solution. You have this works for every x in the real line and for every t positive. This is the D-D'Alembert's solution of the wave equation with the initial data. So, you once you are given, if you are given initial data, that is fx and gx on an infinite string, initial displacement and its velocity of the string all along the infinite string, if you know at initial time, that is at t equal to 0, you can actually find for all times what is the displacement of this string. For all times you can get it from this formula. So, that is what is the D-D'Alembert solution This is how you can, so what you have is if your domain is infinite one dimensional wave equation is actually second order linear partial differential equation in two variables, so that is t and time and spatial variable x, but spatial variable is only one dimension, so that is why you call one dimensional wave equation. So string can be 0 to infinity, semi infinite also it can be, so you may have one side 0, other side is infinity. If you have infinite semi infinite string, okay, so wave equation in the domain x belongs to 0 to infinity, okay, t is positive. If in this domain, if you want to work, so again you have the wave equation you have to write, that is utt minus c square ux x is 0, x is in now, x is simply positive and t is positive. So this is the semi infinite string, okay. Now what is the, this is the equation, this is the wave equation, one dimensional wave equation. A domain is again you have a t, so you have a time domain, so initial data you can provide. What is your initial data? U at x 0 equal to fx. This is what is your x is only from x positive, so this is given only for x positive and its velocity ut at x equal to 0 is gx. So what is the domain? Domain is 0 to x, there is the boundary, this is the boundary, and also at x equal to 0, this is all along the t, this is also boundary, okay. So at t equal to 0, this line, this boundary is the initial data you have to provide physically. Here at x equal to 0, for all times you have to provide a boundary data, okay, because this is known, this is at the boundary, this is the boundary point is only 0, okay. So the boundary point is 0 and you have other boundary, spatial boundaries at infinity, so you do not have boundary there, so only boundary is at x equal to 0. So this is the initial data. Initial data is again as usual, you have two initial data you have to provide because the second order, okay. Now for the, because you have the boundary here, okay, you have only one boundary data you have to provide. Spatial data means spatial variable you have to provide, you do not have to provide just because you have two second order, you need not provide two values at x equal to 0, okay. So just for the boundary data, that is why for the spatial variable, that is actually physical boundary, on that boundary you provide a data, you should, the displacement should be known, okay. So what is that boundary is at x equal to 0 for all times t. So on this boundary you provide what is your u at x 0 t. So this should be known. So if you provide this u at x 0 t, either this or you may be you may want the flux, that is u, what is the derivative of with respect to x at 0 t, either this or this you should provide, okay. With the second order or the combination of this you can provide. So either u at 0, u at x equal to 0 or ux dou u by dou x at x equal to 0, either these two or combination, that is how you can provide. So you can see first start with this, let us say u is given at x equal to 0, okay. If u is 0, suppose you fix it, that means a displacement, you fix one end of the string, you fix its displacement is 0, then for all times, okay. So this is boundary data. So or the boundary condition. So these are the boundary condition, together this equation along with this initial and boundary data forms a boundary, initial and boundary value problem for the wave equation in the domain x positive. So how do we solve this? By looking at this, only extra thing is boundary data, okay. So if you actually see, when do you, if you have for x positive, you want to find for x positive, you try to extend this, you try to extend this string into you extend as a function u of x t x positive is to be found. Okay. What I do is I try to extend these functions, okay. All the initial data f x, g x and this u I try to extend, okay. I try to extend in such a way that it is an odd function. If it is an odd function, for example, you take some function f x which is defined x positive side, f at negative side I define it f x is minus f of minus x for x negative side. So, that means for negative side I define it as odd function, okay. I extended this function as an odd function. I extended f is known only here now. Now, using the data here I extend it to the negative side. That means for x negative I simply take minus of f of minus x, because x is negative, so it is positive, that data I know, here I know. So, f at negative side is defined based on the data here. If you have a data here like this, minus of this, okay. How do we do this? How do we get? So, let us say simplify. So, it is simply constant function, let us say f x equal to 1 minus 1 is the odd function, something like this you extend it, okay. So, extend u x t f x g x as odd function, extend to x negative side as odd functions, okay. How do I do this? So, that means u at x t equal to u of x t if x is let us call this u, okay. Extension function is u1 now. u1 is u of x t for x positive, okay, for all times. Nothing is t means for all times this is true, okay. And now I use minus u of minus x t for x negative side. This is how I extend. This is how I extend my function u of x t, okay, as an extension. So, similarly you can get u of f1 of x as f x for x positive minus f of minus x for x negative, okay. And similarly this one on g1 f x, these are my extended functions, that is g x for x positive minus g of minus x as x negative. What is the advantage of by doing this? By doing this you can see that now try to use u at 0 t equal to 0, okay. Now, if this is 0, if you want this function to be continuous function u1 of x t, u1 of x t you want to be continuous function. So, u1 of x at 0 t 0 positive, okay, positive side you take, that is what is this, right. This is the u at 0 t means you know only positive side, this is 0. So, at this limit u of x t as x goes to 0 plus, that is 0, okay. So, this is same as u1 of x t equal to 0, okay. And if you want this u1 to be continuous, this has to be same as u1 at 0 minus t, okay. So, what is this u1 at 0 minus t? That is no, so not like this. So, let us say, so if you want to make u1 is u1 of x t is continuous at x equal to 0, okay. If you want u1 is continuous and it is differentiable, you extend it in such a way that it is it's smooth, okay. It is not like the example I shown, you do not take this continuous function, so that you see it is discontinuous here, you extend it in such a way that it is continuous like this, okay. It is also differentiable, because it has to be, if you want to make use, what you are trying to do is, idea is to extend this domain from 0 to infinity to minus infinity to infinity, so that the extended functions will also satisfy wave equation. So, that means it should be differentiable. So, you have to extend in such a way that they are differentiable. So, simple continuity and differentiability. So, you want this to be continuous. If you want simply to be continuous, then what has to be done is u at 0 t should be same as minus u at minus 0 t. Okay. That means this is same as minus u at 0 t. That means simply u of 0 t equal to 0. This is naturally satisfied already. This is the boundary condition is given. Okay. So, this is naturally satisfied if you do this. Boundary condition is already satisfied. Okay. If you choose this extension, this odd extensions of your unknown function is satisfied. So, and you see that u is actually for x positive, it satisfies the wave equation. If you do even here for minus u minus x t, if you take two derivatives is again u x x of minus x t and minus and then what is its derivatives of t is minus u t t minus x t. Okay. They already satisfy, they satisfy this is defined for x positive, right, x negative. Okay. So, they are together. If you put c square minus c square and then plus this and minus this is nothing but minus of u t t minus x t plus c square u x x minus x t. Okay. This is x negative side. So, you see that these are all well defined. This is u t t, this is a wave equation for x u, wave equation for u satisfied by u in the positive domain. Minus x is negative, that means minus x is positive. So, this is 0. So, u this quantity for x negative is also satisfying wave equation. Okay. Now, you assume that they are smooth enough, u x x, u t t, they are all continuous at x equal to 0, then u 1 is also continuous form, u 1 is also satisfying wave equation. So, assuming u x x and u t t are continuous, sorry u 1 dou square u 1 by dou x square and dou square u 1 by dou t square are continuous at x equal to 0, we get what we see is by assuming that they are continuous, what we are seeing is there u1 of x t satisfies the wave equation, that is dou square u 1 by dou t square minus c square dou square u 1 by dou x square equal to 0. Now, u 1 is defined for every value, even for negative side. So, this is defined for every value of r. Okay. They are continuous. So, u 1 is now, because they are continuous, not only they are differentiable, the derivatives are also continuous. So, it is u is itself is continuous. So, that means boundary condition is automatically satisfied. So, you have, if you extend this your u, f and g as an odd functions, this boundary condition is automatically satisfied, then u and u1 is automatically satisfy the wave equation. Now, what happens to your u1 at x equal to x t equal to 0? u1 at t equal to 0 is what happens? u1 at t equal to 0 is u is nothing but u1 at x 0, that is u at x 0, that is f x minus u at minus x 0, okay, for x negative. So, that is nothing but f of minus x. Okay. This is exactly u1 at x 0. If you see this, u1 at x 0 is u at x 0 is f x, okay, minus u at minus x 0, that is x negative side means is actually nothing but minus f minus x negative. So, exactly both are same. Okay. And similarly, this is dou u1 by dou t at x 0 is g1 x. So, what is dou u1 by, so the time derivative of u1 is ut at x0, that is gx x positive minus ut minus xt at t equal to 0 is minus g of minus x. So, this is how this is what it is. You have a boundary data for every x, for every real value. Now you have the data. So, you can write here. So, u1 at x0 is, now what is that function? That is fx, f1 and g1, f1 of x. Now this is for every real line, and similarly dou u1 by dou t at x0, this is now g1 of x, that is for every real value. So, now this is like earlier problem, boundary condition is automatically satisfied. Okay, this is automatically satisfied. Making use of this initial data, we simply extended these functions as an odd function, so that the boundary condition is automatically satisfied. Now what you have is simply wave equation on the full real line, that is whose solution we already know. Okay, that is D'Alembert's solution. So, this implies u1 of xt is nothing but half of this data f1 at x minus ct plus f1 x plus ct plus 1 by 2 c integral x minus ct to x plus ct g1 of s ds. This is what is your solution u1 of xt, but you want u of xt. Okay, u of xt you want u at xt x positive. Okay, for x positive we want u of xt. So, what is my u of xt for x positive? This is simply u1 at x positive. Okay, u1 at x positive is u of xt is simply whenever you have x positive. So, you have two cases. When x is positive, this has to be, you do not know about this one. Okay, what happens to this function? So, you want we want x, u1 is actually equal to u1 at xt for x positive. Okay, what is this one? This is actually equal to, you have two cases. One is when x is 0 and less than ct, in that case x minus ct is negative. Okay, you can see that when 0 is less than, x is between 0 to ct, f1, that is my u1 of xt. Okay, f1 is a negative. So, x minus ct, this ordinate of this function f1 is negative. So, if this is negative, what is when x minus ct is negative, what is that? Minus, it is actually minus half, or rather you write half times minus f of minus x minus ct, that is ct minus x. Okay, plus when x is between 0 to ct, x plus ct is always positive. So, you have simply write f of x plus ct. This I am writing from this using this one, this function. Fx is x positive. If it is negative, you have to write minus f of minus x, that is your f1x. So, if you do this, this is what I wrote. For u1, f1 I wrote, f1 as this one, and now for f1 x plus ct is this term. Now, the remaining is plus 1 by 2 c, and this one x minus ct, you split this into x minus ct to 0 g1 of s ds plus 0 to x plus ct g1 of s ds. Okay, this term I split it like this, but I have to write in terms of g and g only, not g1. So, when x is between 0 to ct, x minus ct is negative. So, clearly g1 is negative side. So, I have to replace this with minus g of minus s, okay, because x minus Ct is negative, negative to 0. So, that is g is negative, g is defined, okay. So, that means g1 is negative, s is negative, okay, s is negative. So, it has to be g1 of s is negative is g of minus s, minus of g of minus s, that I put it here. So, this is simply g1 is g of s when x plus Ct is 0 to x plus Ct, s is always positive. Now, what is the other term is half. Now, what is left is you want x positive side. So, the x is greater than Ct, okay. When x is greater than Ct, f1 is always positive, this is also always positive. So, you can simply write as usual f of x minus Ct plus f of x plus Ct, and this also 1 by 2 c integral x minus Ct to x plus Ct g of s ds. And so, because you again like you split it like this, g1 of s between 0 to between x minus Ct to 0, s is always positive, that is why I am replacing g of s, g1 of s by g of s only. Similarly, 0 to x plus Ct, s is still positive. So, this is the case. So, combining it together, so there is no negative sign. So, x is greater than Ct, this is what you get. So, if you combine it, if you rewrite, simplify nicely, so you have nice form here. So, this is half times f of x plus Ct minus f of Ct minus x. Now, this you can combine it. How do you combine it? First, you change the order of first you change the variable minus s as s, okay. If you do that, just replace, so what you do is let s this x minus Ct to 0 g of minus s ds, this will be same as Ct minus x to 0 g of s ds minus, okay. I simply change s by minus s, okay. If you do that, g of s ds will be minus ds, you have to replace this integrands, okay. So, or put s equal to t minus t, if you do, so you have to write gt dt, or if you call the s1, okay. So, t I already used, so you have s1 ds1. So, this is what you will get. So, now again you change this dummy variable s1 as with s, what you have is simply 0 to Ct minus x, okay, 0 to Ct minus x and 0 to x plus Ct, 0 to Ct minus this is exactly equal to 0 to Ct minus x g of s ds, okay. So, the whole thing what you see is you have 2 by c, 0 to c to x and 0 to so minus, you have a minus. So, minus means this is going to be plus from c2 minus x to 0 g of s ds plus 0 to, so you have 1 by 2 c is common here. So, you can combine it. So, you have 0 to x plus Ct g of s ds. So, this together you can write, you do not have to, so you can combine it and say x plus Ct, okay. So, this is what you have from x less than Ct, otherwise half f of x plus Ct plus f of x minus Ct plus 1 by 2 c x minus Ct to x plus Ct g of s ds for x greater than Ct. So, this is your general solution, not the general solution, this is the solution of initial boundary value problem in the semi infinite domain x positive, okay. So, this is the solution, this is the required solution, this is the required solution. So, you see the given data is f and g is known, you know for all times what is your u of x of t. Okay. You have the displacement for all times if you, even if it is given on semi infinite domain, that is 0 to infinite string, semi infinite string, but the one end of the string is fixed, that means displacement is 0. This is how you simply, the idea is simply extending these functions as odd functions, but in a smoother way. Okay. You extend it in a smooth way, so that it automatically satisfies wave equation and the boundary conditions, so that you can write, you can make use of your solution, D'Alembert solution, to write its solution here. Okay. So, we will also see, we can in the same way we can also see if your boundary data is Neumann data, that is ux, instead of u0 of t, if you have ux at 0 t is given here at x equal to 0, that means what, ux at 0 t, that means the slope of the string at x equal to 0 is 0. Okay. That slope you can you fix in such a way that the slope of the string is 0. Okay. If you give this 0, this condition, instead of this if you give this condition, how do we solve this? So, only thing is same domain wave equation, initial data is same, now the boundary data you are changing to this type, then only idea is only simply extend the functions as uneven function, so that this is automatically satisfied. Okay. So, this is how you can actually solve these two types, either this or this are given. If this is given, you extend this u and given f and g initial data, you extend them as an odd functions. If your boundary data is ux at 0 t is 0, then you extend these functions, unknown function u of x t and initial data f x g x, you extend them as even functions, okay, in a smooth manner, so that they automatically satisfy the wave equation and the boundary condition. Okay. So, that you can make use of D'Alembert solution, maybe that we will see in the next video. So, I will try to see that one, and what are the other boundary conditions we can give at x equal to 0 in the semi infinite domain. We will see that in the next video. Thank you very much.